Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, well, hello. My name is Rowan McAllister, and I'm a third-year PhD student at the machine learning group, supervised by Carl Rasmussen, and I'm going to talk a little bit about our research in learning to control. So I'm going to break this talk up into 5 main points. First, I'm going to talk about control, a general framework for control, a very simple one. And then second, how we can learn within that framework. Thirdly, how we can incorporate filtering into our control to help us out with observational noise. And then fourth, how that affects the learning to control by using filtering. And then at the end, we'll have some fun videos of the experiments. So first up, I'll talk about control. So as way of introduction, consider you've got some nonlinear dynamical system, such as the cart pole. It could be anything, but for concreteness, we'll go with this. So the cart pole is constructed such that a cart can move along in an X direction, and attached to the cart is a frictionless is a pendulum with a frictionless pivot, and that pendulum is free to swing around. And we can also apply some forces in the X direction as well, in which to influence the system. And the goal of this, our goal here is to be able to invert the pendulum, which starts off in a downwards position, and be able to balance it upright at an origin. And the control task here is, how do we apply forces in which situations that the cart pole is in, such that we can achieve our goal. And this system is not so trivial in the way that we can't just use some linear controller to solve it. We can't just use some PID controller. It has to be a little bit more complex than that due to the nonlinearity of the dynamics. Okay, so what's a more solid framework for that? Well, we can start off by writing down the latent state of the system. For the cart pole, this, to fully describe the dynamical state of the system, all you need to know is x, the position. You need to know theta, which is the angle of the pendulum, and the time derivative of those two. With that information, you can predict how the system will evolve. So we start off with this, and then we've got some noisy sensors, which are giving us data on this system. So we've got some y, which is related to x, except it's got some noise added on. And from y, we're going to make a decision, given by the rectangle box u, about what force we're going to apply to the cart in order to control it. So this force, as well as the current state of the dynamical system, will define how the system evolves in the next time step. And that's according to some unknown latent potentially nonlinear function f. And being a time series model, the whole process repeats. Okay, great. So this is how we can control a system. But what if we start off in the position where no one's given us a control yet? No one's told us what that mapping pi is. And additionally, we have no idea of f. We don't know physics at all. What can we do? Well, so our approach is to, first of all, to start looking at f. And to say that if we can train a probabilistic model on the potentially nonlinear dynamics function f, what we can do is we can make predictions about future dynamics. And ultimately what we care about is long-term dynamics, which we might not be able to learn directly, but what we can learn is short-term dynamics from one time step to the next. And so the ability to make sequential predictions from one time step to the next will allow us to simulate how the system might evolve from now up until some time horizon far away. So this brings us into learning control, and the simulator for us plays a critical part. So the only difference between our simulator and what's happening in the present reality is that in the present reality, we have these specific truths about the state of the system X, which we can't observe directly, but we do get a specific observation read out by our senses. And from that, we have to make a specific decision about how we're going to control the system. So the only difference in simulation is that there's many ways that this system could evolve. So we use an analytic framework of Gaussian distributions to capture this, and this is opposed to something like particle filtering. One of the reasons we do this is that associated gradients are nice and easy to compute and very smooth. And one of the philosophies that we stick with is that a good simulator must reflect reality. So that means in the distribution of simulated variables x, y, and u, we would be acting precisely as we would be acting in reality. So for instance, in reality, this is closed loop control. So in simulation, it better be closed loop control as well. And this is opposed to other methods such as model predictive control, which do operate closed loop in reality, but open loop in simulation by pre-computing future actions up until some time horizon far away. Okay, so why is this useful? Why are we talking about a simulator? So a simulator is valuable to us because it means you can dream up any particular controller that you might like to try next, or any particular parameterization of a controller. And what we can do is we can run that through the simulator and see how well does that control your system. Does it control it well or not so well? And we can pick the best one and then try that on the actual system. Okay, so what's a more concrete way of saying exactly that? So what we first do is we define a controller. We define a controller's functional form, which is fixed. And there's a particular parameterization theta that we're trying to find. And the controller takes in that observation together with a parameterization and outputs a control signal. Okay, so with our simulator, what we can do is we can simulate from our current position, x naught, up until some future time horizon. X horizon. And so with what we can now do is we can evaluate the controller by taking an expected summation of discounted costs from now up until the horizon, where the expectation is over possible future evolutions that the system can take from now on up until some future time horizon. And we can also get gradient information from that, which helps us to optimize the controller. And so with respect to all the data that we've seen so far, we can come up with a particular locally optimized parameterization for our controller, which we can then try on the system. Okay, so that's a method to learn how to control. And what I'll talk about next is control with filtering. So if we go back one sec, one of the problems that we have up at the top there is, say in the cart pole example, say that the cart pole has managed to swing up this pendulum and it's currently balancing it at the top. A good controller in that region of the state space will effectively learn high gain parameters where it knows that if the pendulum starts to fall, it's very quickly got to get the cart under the center of gravity of the pendulum before it starts to fall past some threshold, and then the cart can't catch the pendulum anymore and the pendulum's swung down and the system's totally destabilized. So one of the problems with that is if we've got any kind of reasonable amount of observational noise, that's getting injected directly into our controller through these high gain parameters and produces wild variations in U. And that's how we're affecting the system. So with wild variations in the output of the controller, we get wild variations in the state of the system. All right, so we can fix that with some filtering. All right, so what is filtering? So filtering, same kind of graphical procedure as before. We start off with a latent system state X, but we also start off with some filter state, a prior belief about the state of the system. As before, we get a noisy observation. And what we can do is we can combine both sources of information, our prior belief together with an incoming observation. And together that can form a updated belief about the state of the system, which we can input into the controller to make a decision about what we're going to do. Now, the good thing about this is that the controller can now make a better informed decision, and it's also a much smoother signal owing to the combination of both these sources of information before input into the controller. And then, as before, control with the latent state of the system defines how the system will evolve. And the last step is that because we know that this is going to happen, we can update our belief about the system together with the action that we took to define a predicted belief posterior about the state of the system. And the time series continues. So, all right, so we're almost there. We've filtered our signal, but the last thing left is that our simulator, if we leave it as it is now a bit out of match with what's happening in reality. We haven't yet told the simulator that what we're doing is we're going to be filtering the system. So to make it a realistic simulator, what we'll do is we'll go back and we'll say, okay, so in present reality, what we had is this belief distribution about the state of the system. And that's going to affect you, and in the next time step, that will thus affect X, and Y. So it really is going to affect our system, so we better tell the simulator that. So the difference here is that X, Y, and U are the same as before, but with our belief posterior, instead of, say, having a delta function around the mean of our belief, we now generalize that to say, okay, there's potentially different means that define our belief posterior that happen in the future. And just to make things a little bit easier, rather than having a distribution over the matrix over this matrix that defines our variance of our belief, we just take that as static across all potential futures, just to make things a bit mathematically simpler. Okay, great. So I think So now I'll get into some of the experiments. And I'll first of all start showing you a video of the system training. So first of all, it starts with zero prior knowledge about physics, and also the controller is completely not trained. So we'll see in about 4 or 5 trials, the system will eventually learn what to do. So the goal is that cross at the top. That's the origin. And this green bar here is to give us an indication of the applied force that we're applying to the cart. And what we'll see is a gold bar come out where that immediate reward is, to give us an idea of how close the end of the pendulum is to our goal there, which is the cross right at the top. So I'll play that, which is not open. All right, so initially it doesn't know what to do. It's just trying random actions. The second trial, it kind of got a hint of what was there. It got a reward up at the top there. So third trial now, it's starting to replicate what it saw there. And by the fourth trial, it's almost got it. And by the fifth trial, it does pretty well. So now if we take this controller and then run that many times once it's trained, what we can see is independent of the start positions of our variables, say x or theta, over time they converge to x, the origin 0, and also inverted, which is 2 pi up the top. And this is completely unsurprising to our the confidence bounds that our simulator is giving us described in blue. So now I'll show you a no-filter controller with significant observation noise. So x, we've got 4 centimeters of uncertainty given by And we can see that uncertainty in the end of the pendulum given by that bound, that blue kind of ellipse on the end. So it's kind of just on the edge of being able to control it. So if we ramp up the observational noise standard deviation to about 6 centimeters and 6 degrees, this is now kind of just getting off the cuff in terms of what a no-filtered controller can handle. And you can see it's not quite being able to control this thing. All right, so now we can talk about that third or fourth step where we say, okay, let's fix that policy, but let's just help it out by filtering the observations that it's getting. So it does do a little bit better. We haven't yet told the simulator that we're doing this, but we're just helping it out by filtering those observations. So it does a bit better, but it's not until we really go back and tell the simulator that this is what we're doing without collecting any more real-world data, but just re-optimizing that. And now it does much better. It's sticking to that. At least within the width of that cross there each time. So yeah. So and that's basically because our simulator is now much more realistic with respect to what's happening in reality. And that's about it.
We have time for questions. Yeah, Zubin?
So what are the challenges to scaling this up to bigger problems?
Scaling this up to bigger problems. So I think this currently, in terms of higher dimensional problems, I think this currently scales quadratically. So one of the things that we've been looking at is how to, we compute a lot of covariance matrices, and so the off-diagonal terms, we've been looking at ways to come up with approximation techniques to effectively make it linear with respect to how many state variables we had. In this case, we had 4, but to really scale it up, that's one way of making it at least approximately linear. Yeah, so we've started to test that out now, and we've found what you might expect. It, at least with an approximated filtered simulator, it does a lot better than without using a filter at all, but not quite as good as if you compute everything exactly. But it's not far off the mark, so I think those approximations are potentially the way to go. Yeah.
What about the off-policy case, where you have a few examples of somebody demonstrating it, for example, or a good instance is that is it a prior observation and everything goes through as is, or does it require modification of the method?
Do you mean is it off policy that it doesn't matter where the data comes from?
I can give you some, like for example, the small card. Like you can make a video game out of it, and you probably get 100 really good human-controlled instances where they control the card very well. Can you somehow use that? Is it just like?
Oh yeah. It doesn't matter. It doesn't matter how you generate the data. It's I forget the reinforcement learning terminology if it's off policy or on policy, but it's independent of what generated the data. Yeah. So in the last example, we actually used data from the no filtered controller, but the filtered controller once we told the simulator that that's what we're about to do, it didn't care about where the data came from, just as long as it had data. Yeah. Yep.
So what happens when you apply this to an actual real-life system rather than the assumptions that you have for the simulation?
Good point. So, so that's something that we're going to try next to kind of weed out these kind of more pertinent issues that we might be overlooking in simulation. So, I think one thing that happens in reality is you often get a bit of delay between what the signal is when the signal reads and when you actually get the signal, it might be a few milliseconds after the fact that it's happened. So one way that we've been able to at least deal with that now is by incorporating some of the old actions into the representation of the state. So even though there's this mismatch between an observation and applying a control, at least it had some idea of the control that it was applying previous to the new observation coming in to kind of help the Markov assumption a bit more.